when we have high, we cannot change independently volume fraction and size. They are actually connected together, most probably because particles start more coalescence when you have a higher volume fraction during sintering. We can then take this further to degradation experiments where we are looking what happens during nickel coarsening. These are experiments that were done in a humidified forming gas. So you see actually in this zone 2 and zone 4 how over time the average size is changing. So you have fast grain growth in the beginning, and then here nickel is not growing anymore, but we have different other processes. There is evidence for volatilization of nickel and also formation of surface layers of CGO. But the nickel grain size remains the same. Now I was only looking at this side, and I want to correlate this with second order parameters. I think okay. Surfaces, for each of the phases we can measure the surfaces. Important is we can also distinguish, for example, the pore surface is split into two interfaces. And since the nickel is the coarsest, it has the smallest surface, and then, for example, the pore nickel interface is actually much smaller than the pore CGO interface. And that's actually, this is the catalytic active interface, and that has some impact on the performance. This seems to be very limiting factor for the formation of the TPP. So we can also measure the TPP in this graded microstructures, looking how TPP changes with volume fraction. It's actually a complicated pattern. Most probably it's strongly correlated to the most coarse phase, the nickel, but as we change the volume fraction of nickel, we also change the particle size. So it's not so easy to establish these relations between TPP and volume fraction particle size. In contrast, the TPP is very strongly correlated with this interface between pore and nickel. So it seems that this interface really is a limiting factor for the TPP formation. Now when we compare this with modeling, these are our TPPs in the real microstructure, and the problem is when we do modeling we can change volume fraction and keep the size constant. So this is at lower particle size. Here in this evolution we have changed the composition, but we also have changed with the volume fraction the sizes. So when we could keep the size constant, the model would predict that the TPP would evolve something like this. And with the degradation experiment we can also see how change of particle size has an effect on TPPs here. TPPs, and TPP is this line, is strongly correlated again with the surface of nickel or with the interface of pore nickel. We also see that TPP and the surfaces are changing during the phase where we have grain growth, but then here when we have grain growth, there is actually a change of the TPP which is not related to grain growth. This is most probably due to these, I go directly to this, you see here, in the first phase we have this grain growth, and in the second phase we have an organization where nickel becomes volatile, and where we have the formation of these surface layers, which also leads to a reduction of TPP. So, conclusion, simplified geometries give us strengths. I consider these strengths as qualitative. When we want to go to more realistic structures, FIB gives us a way to go there, but I think we can also use the size distribution information and have synthetic microstructures more realistic size distributions. And then what Thomas Hocker is going to show is that these more realistic synthetic microstructure we can use as a basis for finite element modeling. And why not using directly FIB data? It's simply because we have to reduce the data demand. So I think with this I'm stopping.
Thank you very much, Lorenz. Presentation for questions.
I think you suggested at the end that some of the nickel coarsening was due to volatilization. Could you review again what the conditions were and why you think it's volatilization?
I see that in our analysis here, I see actually from 1000 to 2000 that actually the amount of nickel is reduced. We have lower amount of nickel, and this experiment was done at quite high water content. So it was forming gas with water, I think in the range of 60% water, so quite high.
What was the temperature?
950 degrees. And so what we get here is actually, I think small particles are somehow going away. I don't know where, but then we get a passive enrichment of the ceramic phase because nickel is going away. The pores remain stable, so maybe there's some volume decrease as well. And then because we have higher amount of ceramic phase, the ceramic phase start covering the surface of the nickel more. This also leads to a reduction of the TP without change of grain size. That's how I would interpret the data.
If I interpret the image correctly, it looks like the nickel has just moved from here to here.
Actually, in this phase, in this zone here, you have lower amount of nickel as well. Yeah. It's not that you just have nickel from here and enriched. It was not a cell which was under current. It was just exposed to gas flow at elevated temperature.
Another question? I have one regarding your PSD, the discrete and the continuous one. As if I remember correctly, all of the data presented here is using a continuous PSD.
Yes.
Okay.
Yes.
And you spent quite a bit of time developing methods to make a discrete PSD. Did you end up using that for anything? And if you did, what is the actual meaning of the discrete PSD in these coarsened structures from an electrochemical point of view?
That's a difficult question. The meaning of so what I can say is I did in this sample here. This sample for each zone I did discrete and continuous, and it's really you have a very different geometrical perception, so your result is very different, but the ratio between the two remains constant. It is 2.8. So when you measure a volume and the radius with discrete, that's much larger than when you measure at each point like the shortest distance, what actually is the continuous.
Probably because you have more shortest distances compared to large diameters.
Yes, yes. And yeah, I mean, since the proportion seems to be consistent, consistent, I would say the meaning for the electrochemistry or the impact on the TPP must be the same, like